Hi everyone. This is a little speech from Ryan. Today we are going to talk about ista. It is a method that is aimed to solve the large scale and differentiable optimization problem. So the motivation of the ista is that if we are given this optimization problem, which is addressed in two parts. The first one is quadratic term. Typically, y is something that we observed. X is something that we want to estimate, and h is simply some function that change x into something else, and we observed this change from y. And also, there's another term that is typically indifferentiable. And here we're using the simply L1 norm function. And this problem is really an indifferentiable problem. So it is typically cannot be solved easily by the method we are commonly used, like gradient descent. And it is even so when it is a large scale problem. So how to solve this problem? Before we are talking about how to solve that, let's look at another problem, which is very similar from before, except that there's no edge here. Y, the observed value, and the thing that we want to estimate is actually uncoupled, meaning that all coordinate of x is independent with each other. So if we are given this problem, then it can be easily solved by just optimize each coordinate of x, and which is simply just the soft function of y, and the soft function is defined like this. It has a parameter of lambda over 2, and this lambda is the lambda here, and the function is really a shrink function that shrink that very small value of y into 0, and the big value of y keep similar as it is before, meaning that if y is very big, then it will be has some value, and if y is very small, near 0, then the estimate x will be 0. So this function can be easily solved. How this problem is linked with the problem that we want to optimize. So it turns out that this function, the problem that we want to optimize, can be solved iteratively using the method that we talked previously. The idea is that if we are given a function looks like this, which is basically undifferentiable, here is undifferentiable point, and if we can change this function into something else that has a property that at a given initial point of x, the generated function, which I write here in red line, is always bigger than the original function, and also that at the x0 point, the generated function is conjugate, is tangent with the original function. Then we can see that very intuitively that this red function has a minimized point, and this point has a trend that is getting closer to the actual optimal point of the original function. So just by iteratively using this transfer method, we can get eventually we can optimize the x using this idea. So how how to get this red line function. It turns out that it can be easily add an always positive term, which looks like this. It is something like a quadratic function, and here in the middle, this matrix is definitely positive function, definitely positive matrix, which guarantee that the output of this function is always positive. And also, it has this additive term has a property that if x is equal to the initial point x0, then this additive term will become 0 at x0. So after adding this function, after adding this term, we can get the red line function that that has a property that we talked before. So after adding this term, we get this red line function, and by solving the optimum value of this red line function, just by taking gradient of x, and we get this one. I'm sorry. The idea is that after adding this term, then after some derivative, we can get this term, this function, which basically is just after some manipulative of the values. And here we can easily say that it is basically very similar as we talked before. Here is L1 norm term here, which is the same here, and there is another quadratic term, and this quadratic term is uncoupled, meaning that the x and y is the all coordinate of x is unrelated. It is if we really look into that, we can see that x is this x, and y we can this monster, this big term is actually equivalent to the y here previously. So the solution of this optimum function can be easily solved by the solved function, which we can just plug the y here by using the squared term here. We just plugged in the y here, so we can solve this red line function and solve the optimum value of x, which we call it x1. So this is really how ista update the value of x, and by iteratively update the x. So the next time, the initial point will be x1, and following the same procedure, we can get the next update of x. And initially, this function will converge to the actual optimal value of x. So this is basically how ista work.